In the monstrosity of the universe, mankind has simply started to investigate, notwithstanding our obliged appreciation. We've frequently estimated on the presence of life beyond Earth, sometimes contemplating whether we're singular in the universe. But a earth-shattering situation transpired with the appearance of our first interstellar guest, Oumuamua, an element not at all like any we've experienced, stirring wonder about the obscure domains past our planet. Quite the regarded astrophysicist, Neil deGrasse Tyson, has recently uncovered never-before-seen, declassified pictures of Oumuamua, mixing interest in who sent this extraterrestrial emissary, the meaning of the object's impact, and its association to Oumuamua, leaving on an extraordinary journey into space's profundities. Directed by astrophysicist Neil deGrasse Tyson, we reveal the riddle encompassing this unconventional interstellar drifter. In 2017, an uncommon find using the Pan-STARRS 1 telescope by Rob Warwick acquainted us with an object hurtling toward Earth. The presence of Oumuamua touched off an intense change in our understanding of space and its interminable, conceivable outcomes. Notwithstanding its distinction, our knowledge of Oumuamua has stayed meager, considering public interest. Neil deGrasse Tyson unveiled previously secret, highly classified pictures of Oumuamua, through his ability, revealing its critical influence on our planetary system before digging into the secrets covered in these long-disguised images. It's important to appreciate the captivating substance of Oumuamua. On October 19, 2017, the Hawaii-based Haleakala Observatory made an original observation of what appeared to be a comet or asteroid. However, it was later recognized as the first interstellar object identified within our solar system, other than dust grains. Its unconventional orbit and quick speed suggested its extraterrestrial origin, earning it the name Oumuamua. To understand its structure better, space experts have contrasted it with similar planetary system objects, like the asteroid 25143 Itokawa, which the Hayabusa spacecraft visited in 2005. While Itokawa shared some features with Oumuamua, the interstellar visitor's unique elongated shape and absence of a tail set it apart, adding to the mystery. What also separates it is Oumuamua's remarkable acceleration, much like a bicycle suddenly speeding up without pedaling. Entering our solar system from above, it came surprisingly close to the Sun before continuing beneath the planetary plane, maintaining an extraordinary speed of around 196,000 miles per hour, characteristic of significant dynamic energy. This speed is unrivaled by any human-made object, highlighting Oumuamua's special path through our solar system. The high speed of Oumuamua has prompted a theory suggesting that it could have originated from a binary star system. This hypothesis suggests that gravitational interactions within such systems can provide high speeds to objects. If Oumuamua did indeed come from a binary system, the gravitational forces from the stars could have propelled it on its interstellar journey, explaining its surprising velocity. Beyond its speed, studies have uncovered fascinating details about Oumuamua's composition. It features a dense outer layer, likened to an interstellar shell made of carbon-rich materials, set by cosmic radiation during its long journey through interstellar space. Beneath this protective exterior, Oumuamua reveals its surprisingly dense interior, primarily made of rock, perhaps containing metallic components. What makes it particularly intriguing is the absence of water or ice, distinguishing it from typical comets or icy celestial bodies. Additionally, Oumuamua's surface has a reddish color, a result of prolonged exposure to cosmic rays over countless years. Several individuals have called for contributions from prestigious specialists like Neil deGrasse Tyson and Michio Kaku regarding Oumuamua. Curiously, Neil deGrasse Tyson refrained from commenting on the situation until significant evidence emerged. The release of new declassified photographs has sparked widespread anticipation of his viewpoint. Some scientists propose that Oumuamua's elongated structure, indicated by its light curve, suggests it may be a fragment of a larger body. If Oumuamua detached from a larger object due to a collision or other violent events, it could have gained significant speed during the separation process. This would imply that Oumuamua's speed is not inherent to its nature, but rather the result of past occurrences. Examinations can be drawn with comets and asteroids in our solar system, which navigate at different speeds. While some comets can achieve speeds similar to Oumuamua, they typically show signs of remaining gas and dust due to their volatile composition. In contrast, Oumuamua showed no such features, distinguishing it from known cometary objects. Furthermore, most asteroids in our solar system move at much slower speeds than Oumuamua. The average orbital speed of the well-known asteroid series, for example, is around 17,800 miles per hour, under a fifth of Oumuamua's estimated speed. This divergence highlights the extraordinary nature of Oumuamua's speed and its contrast with familiar solar system objects. Some specialists speculate that Oumuamua could be more than a naturally occurring object. They suggest it may be a deliberately created construct, carefully designed by an advanced extraterrestrial civilization. According to this hypothesis, Oumuamua's unusual features could serve different functions. Its elongated shape might enhance its versatility during interstellar travel, while its propulsion system could enable precise movement through the universe. Figures like Abraham Loeb, an Israeli-American theoretical physicist and space scientist, strongly support this hypothesis. Loeb even proposed a controversial theory that Oumuamua could be of extraterrestrial origin, suggesting that it might be an artificial object or even a fragment of alien technology. He argued that its unique properties, such as its elongated shape and extraordinary acceleration, could indicate a non-natural origin. Loeb's theory sparked widespread discussion, though many established scientists have expressed skepticism. The prevailing view among most researchers is that Oumuamua is likely a natural object, such as a comet or asteroid, with its peculiar properties being the result of natural processes. Wesley C. Fraser and other scientists utilized consolidated brightness measurements from various telescopes to explore AMU's spin period. They inferred that no single rotation period could account for the observed brightness variations. As a result, the object seems to be tumbling in an irregular rotational motion, something unlike anything seen before. This unpredictable rotation has perplexed researchers since its discovery. Observations by astronomers have provided important insights into AMU's unusual spin. It completes a full rotation every 7.3 hours, which is relatively fast compared to the rotational periods of other objects in our solar system. Furthermore, its brightness varies significantly as it rotates, indicating that different parts of the object reflect sunlight to varying degrees. This unpredictable revolution has baffled researchers and led to several interesting hypotheses. One hypothesis proposed to explain AMU's rotation is the spin-induced outgassing theory. According to this idea, volatile substances beneath its surface are exposed to solar radiation as the object tumbles through space, causing them to sublimate and form small gas jets. These jets act as tiny thrusters, applying force on AMU and making it spin irregularly. Another hypothesis suggests that AMU's tumbling movement could result from a past impact with another object. It's possible that a rapid collision deformed its shape and set it into an erratic spin. However, the specifics of such a collision and the objects involved remain theoretical due to limited observational data. A detailed investigation of AMU's shape, composition, and surface features could provide clues supporting these theories and help researchers better understand its strange behavior. To gain further insight, let's look at other celestial objects that exhibit similar motions. One such object is the asteroid 4179 Tacitus, discovered in 1989, which also shows a tumbling motion similar to AMU. Researchers have proposed several theories to explain Tacitus' irregular spin, including the Yarkovsky effect. This effect occurs when uneven heating from the sun causes the object to gradually change its rotation, eventually leading to a sporadic spin. Another example is Comet 67P/Churyumov-Gerasimenko, often called 67P. This comet, which was discovered on September 11, 1969, also exhibits an irregular rotation. It orbits the Sun and displays a distinctive shape with two distinct lobes connected by a narrow neck. It belongs to the Jupiter family of comets, meaning its origin can be traced back to the Kuiper Belt, a region beyond Neptune populated by icy bodies. Scientists believe that gravitational interactions with Jupiter's massive gravity captured 67P into its current orbit. For AMU, researchers believe that outgassing of volatile substances from its surface plays a significant role in its tumbling motion. As the ice on the comet's surface sublimates due to solar radiation, it creates localized jets that act like thrusters, altering the object's spin. The similarities between AMU and these objects suggest that similar underlying mechanisms might be responsible for their unusual rotations. Further study and detailed analysis of these objects could provide valuable insights into the nature of AMU. The origin of AMU has also been a subject of much speculation. Some researchers have proposed that it could be a fragment of a larger body ejected from its home star system due to gravitational interactions or a catastrophic event. This ejection could have imparted an initial spin to AMU, which has persisted throughout its interstellar journey. The exact process by which AMU was ejected and its subsequent trajectory remains uncertain, highlighting the need for more data and further research. However, it is also possible that AMU is debris from a collision between two objects in a distant star system. The resulting fragments could have been flung into interstellar space, with AMU being one of the pieces trapped by our solar system's gravitational pull. Without further proof, these hypotheses remain speculative. A detailed investigation of AMU's composition, isotopic ratios, and surface features could offer clues about its origin and shed light on the mechanisms behind its peculiar spin and motion. As seen in the images, the absence of visible emissions has confounded scientists even more. This lack of visible outgassing rules out the possibility of AMU being a typical comet or asteroid, presenting an intriguing mystery that requires further examination. There is a possibility that AMU's lack of emissions could be explained by it being a dead comet. A typical comet's icy composition sublimates as it approaches the Sun, resulting in a visible coma and tail. However, if AMU had lost most of its volatile materials due to repeated close encounters with stars during its long interstellar journey, the lack of visible emissions could be explained. The intense heat and radiation from these encounters might have stripped away AMU's volatile components, leaving behind a rocky or metallic body without the usual cometary features. This opens up the possibility that AMU is an interstellar asteroid. If AMU were an asteroid, the absence of visible outgassing could be explained, as asteroids typically don't exhibit the same outgassing behavior as comets. However, the elongated shape of AMU remains a mystery. Asteroids in our solar system tend to have more irregular shapes. Some researchers suggest that its elongated form could result from gravitational distortions experienced during close encounters with a star or planet in its parent star system. Additionally, asteroid Bennu, the target of NASA's OSIRIS-Rx mission, offers another point of comparison. Its irregular shape and behavior may share similarities with AMU's characteristics. NASA's OSIRIS-Rx mission gives a fascinating examination of Bennu, characterized as a crude, carbonaceous space rock. It did not show any apparent outflow during its nearby encounters with Earth. However, this absence of apparent emanation was expected, as Bennu's composition is dominantly rough with minimal volatile substances. This exhibits that asteroids, unlike comets, generally don't display apparent outflow. This aligns with the thought that Oumuamua could be an interstellar asteroid. What were Neil deGrasse Tyson's perspectives on the declassified pictures? After the release of the declassified pictures, Neil deGrasse Tyson took on the responsibility of effectively investigating and explaining the details and possible implications of Oumuamua. Tyson consistently stresses the importance of evidence-based inquiry in his discussions on Oumuamua. He highlights the need to approach the subject with skepticism while exploring the captivating idea of Oumuamua as a message. This approach reflects the excellence of scientific investigation, where remarkable hypotheses are considered, tested, and either validated or disproved. Tyson proposes that the universe may be far stranger and more complex than our current understanding. He also discusses Oumuamua as a challenge that tests our technological and scientific progress. How we perceive, study, and respond to Oumuamua could provide valuable information to its creators about our progress, development, and status for potential contact. This perspective extends beyond the object itself and raises broader questions about our technological and philosophical readiness to understand and interpret such anomalies. Tyson hypothesizes that Oumuamua's unexpected appearance and the ensuing scientific activity it sparked should be seen as a test of our technological abilities. The fact that we could identify, track, and study it demonstrates our growing capabilities in space observation and exploration. Moreover, Oumuamua challenges scientific principles with its unusual acceleration, unique shape, and trajectory, which defy simple explanation. Tyson sees this as a test of our scientific flexibility. Can we adapt our theories and models to accommodate this new data, or will we try to force it into old systems? Oumuamua's brief passage through our solar system required rapid, coordinated efforts from the global academic community. Tyson considers this a test of our ability to collaborate, share information, and pool resources in the face of an unexpected and unforeseen astronomical event. It raises the question of how we responded to this challenge and what lessons we have learned to prepare for future cosmic visitors. Diving deeper into the speculative challenge, Tyson wonders about the broader message behind Oumuamua. If it was purposely sent our way, perhaps the test isn't just about detection, but understanding. Could we decipher a message or signal embedded in its design or behavior? If so, how would we respond? These questions remain unanswered, and the search for answers continues. Another perspective Tyson explores is the real purpose of Oumuamua as an interstellar messenger. Rather than being a simple anomaly or curiosity, could it be a vessel carrying delegates from a distant star system? While this hypothesis might seem like science fiction, Tyson argues that we should consider all possibilities, no matter how extraordinary they may seem. After all, the universe is vast, ancient, and filled with wonders yet to be discovered. Tyson's examination of Oumuamua, whether as an interstellar relic or a mere cosmic occurrence, demonstrates the depth of his scientific inquiry. His approach blends wonder, skepticism, and rigorous scientific investigation. It challenges our understanding of life in the universe, the nature of cosmic objects, and our place in the astronomical tapestry. The implications of Tyson's hypotheses are far-reaching, ranging from technological advancements to philosophical reflections. They disrupt traditional astrophysical theories and could potentially reshape our understanding of the universe. If any of his hypotheses prove true, it would mark a monumental shift in perspective and usher in a new era of space exploration.